Hello, in this video I'm going to be solving exercise 6.4.102 from Jiří Lebel's notes on Diffy Qs. So here we're given this ODE and our task is to solve it subject to these initial conditions. Now what's special about this ODE is this right side right here, this delta t. So this delta t, before anything else, we must recall what this is. Delta t is the Dirac delta function. What property does this function have? Well, whenever you take a function, f of t, delta of t, and you integrate it on any interval containing, in this case, 0. So even more generally, let's say you want to integrate over the most general interval possible. When you integrate this function, then as long as f is continuous at 0, this function, this delta function, when you integrate it against f, as we've done here, it returns the value f of 0. More generally, if you take a function, f of t, and you integrate it against a shifted delta function, so like let's say delta t minus a dt, this instead is going to give us the value at, you might guess, f of a. One way to see this is, roughly speaking, if we do a u sub, if we let u equal t minus a, then du equals dt. So this integral above becomes this. So the limits, as t goes to minus infinity, u goes to minus infinity. As t goes to infinity, u goes to infinity. So the limits remain the same. And then our t becomes u plus a, and then we have delta of t dt. And so this case reduces to the one we had above, where we just need to plug in 0 to this function right here. So this would give us f of 0 plus a, which equals f of a, just as we expect. Okay, but why is this useful? Well, now what we're going to do is we're essentially going to solve this using the Laplace transform right here. So if we take the Laplace transform of both sides, what do we get? Well, we're going to get L of x double prime plus a times L of x equals L of this delta function. And so our task becomes figuring out what the Laplace transform of this Dirac delta function is. Okay. Well, what is this Laplace transform of the Dirac delta function? Well, here we're going to go back to the definition of the integral 0 to infinity e to the minus st delta of t dt. And I know up here I wrote the limits from minus infinity to infinity, but all that really matters is that the region you're integrating over contain the points that you're subtracting by in this delta function. So if we imagine writing this as delta t minus 0 dt, our point 0 is in this interval of integration. And so to evaluate this integral, we just need to plug in this value 0 for the value of t right here. And just to make this drawn out, if we let this be our f of t, then what we're doing is integrating f of t delta of t minus 0 dt which in turn is going to be f of 0 because we're integrating this delta function. But what is f of 0? Well, f of 0 for us is e to the minus s times 0, which is just 1. And thus we found that the Laplace transform of the Dirac delta function is just 1. Okay, now let's go to the other side. As always, L of x double prime is s squared capital X of s minus x of 0. But for us, x of 0 is just 0, so this is just going to be 0 right here. Right here. And similarly, L of x is just going to be, well, I accidentally wrote double primes. My bad. That was my mistake. And I was also confusing this formula. So this will be s x of s minus x of 0. And this will be xs of s. And then this will be capital X of s. And so, from our previous work, we're going to have xs of s. And by previous work, I mean this equation right here. And once again, this is equal to 1 from what we just calculated. So what we get is that this plus a times x of s is equal to 1, which implies that capital X of s is equal to 1 over s plus a. And therefore, when we take the inverse Laplace transform, I guess let me write x of t. If we take the inverse Laplace transform, this is just going to be e to the minus as. E to the minus at, sorry. All right, that wraps up this video. If there are any questions, please feel free to leave a comment. Otherwise, I will see you all in the next video.